started in the interest of time. So once again, thank you very much, Armando, for accepting our invitation to speak at the Subsurface Mechanics webinar series. So once again, thank you very much, Armando, for Subsurface Mechanics webinar series at IIT Madras. It is indeed a pleasure to host you. So Armando Duarte is the Nathan Newmark Professor in the Department of Civil and Environmental Engineering at the University of Illinois at Urbana-Champaign. He received a PhD degree in computational mechanics from the University of Texas at Austin in 1996. Professor Duarte has 5 years of industrial experience. He's affiliated with the UIUC Computational Science and Engineering program. He's a fellow of the United States Association for Computational Mechanics and a fellow of the National Center for Supercomputing Applications. Dr. Duarte has made fundamental and sustained contributions to the field of computational mechanics and methods, in particular to the development of mesh-free, partition of unity, and generalized and extended finite element methods. He proposed the first partition of unity method to solve fracture problems in 1997 and pioneered the use of asymptotic solutions of elasticity equations in the neighborhood of cracks as enrichment functions for this class of methods. Dr. Duarte has published more than 120 scientific articles and book chapters and co-edited 2 books on computational methods. Dr. Duarte's group has a history of collaborative research with industrial partners, ExxonMobil as well as GE, and national laboratories, the Air Force Research Laboratory and FAA in the US. He has received several awards for his research and teaching accomplishments. Thank you very much, Armando, once again for accepting our invitation, and the floor is all yours.
Oh, thank you very much, Chandra, for the introduction. I also want to thank you and Ramesh and the other seminar organizers for the invitation to give this talk. I'm very honored and grateful for the opportunity to share with you the work of my group on 3D modeling of multi-stage hydraulic fracturing and wave propagation in fluid-filled fractures within a generalized FEM framework. So I'll start with a few slides on the application that has driven this research. Multi-stage hydraulic fracturing from horizontal wells is broadly used in shale gas and oil reservoirs. So this slide illustrates a horizontal well with 3 stages of hydraulic fracturing treatment. So this stage has completed, this is ongoing, and this is the next stage. So each stage has between 3 and 8 fractures, as illustrated here, and each fracture starts from a cluster of perforations used to connect the wellbore to the reservoir. And typically this cluster is idealized as a radial notch, like shown here in simulations. Fractures are also assumed to propagate on a plane, which is often not realistic. In reality, fracture interactions and reorientation near a wellbore, like the one shown here, create complex fracture geometries. So this can be seen in the simulation of this problem, where we have 2 transversal fractures propagated from a horizontal well. So as fluid is pumped, the fractures grow, and interactions between the fractures cause them to propagate away from each other, creating a non-planar geometry that shown here. So this induces a strong nonlinear pressure drop near the wellbore, which varies significantly among the different clusters. And this leads to that the majority of production comes from only 20 to 30% of the clusters. So there is still lots of room for improvement of this process. It's now well accepted that the neo-wellbore fracture geometry plays a key role on the performance of multi-stage fracturing. However, the simulation of this class of problem, especially at the early stage of fracture propagation, is a fairly challenging problem. So in the first part of my talk, I will present a generalized 3D finite element method for the simulation of this class of problem. I will present the mathematical model we have adopted and the generalized FEM we have developed. Next, I'll present a validation and an application of the methodology. In the second part of my presentation, I'll focus on a methodology to infer the shape of fractures in a reservoir. This involves the simulation of wave propagation in fluid-filled fractures. These are the so-called Krauklis waves. And I'll present a verification and a validation of the methodology. And finally, the simulation of Krauklis waves in an elliptical fracture. So let's start with the mathematical model we have adopted. So we need to solve the following system of nonlinear equations. The rock deformation is modeled using 3D elasticity equations as listed here. We are interested in ultra-low permeability shale reservoirs, and pore-elastic effects can be neglected in this case due to the time scales of the simulations. So this has been shown in these two references. Fracturing fluid flow and pressure in the fracture cavity is modeled using Reynolds equation and lubrication theory. So in this equation, W is the fracture opening, Q is the fluid flux in the fracture cavity. And this is the relation between fluid flux and pressure gradient. And you see that's a strong nonlinear relation between these two quantities. Fracture propagation is assumed to be governed by linear elastic fracture mechanics. In this equation, K1C is the fracture toughness of the rock, and K1 is the mode 1 stress intensity factor. Again, we are interested in shale, and fracture process zone in shale is much smaller than fracture and reservoir size. For example, in the Marcellus shale, it has been reported that the fracture process zone is of less than 3 millimeters in length. And this leads to a high brittleness number for the problem, justifying the use of LFEM. However, this framework that I'll present could be used with other fracture models, such as cohesive fracture and so on. And finally, leak-off from the fracture to the reservoir is modeled using Carter leak-off model shown here. So we use a generalized and a standard finite elemental method to solve this coupled system of equations. So let's start with the generalized finite elemental method and with some background information on this method. So GFEM can be traced back to numerical methods proposed in the 1990s, in particular, the work of Ivo Babuška, Gabriel Kellos, and John Osborne, who in 1994, they published a paper on a method that they call spatial finite elemental method. So many names were used in the 90s for this same type of method, HP Clouds, partition of unity FEM, extended finite elemental method. But all these proposals, they shared a single idea, which is to use a partition of unity to define approximation spaces. And in the case of these methods, the partition of unity is typically low-order finite element shape functions. So regarding terminology, in this presentation, I call the method generalized FEM, but that also means extended FEM or PU FEM, HP Clouds, any one of these methods. They can also be understood nowadays as being the same, and I'll call that GFEM. So I'll next summarize the main concepts of the method. So this equation represents a generalized FEM approximation of a displacement field U. It's given by a standard FEM approximation, augmented by a generalized FEM approximation. So these functions E sub alpha I are called enrichment functions. And their product with a standard FEM shape function defines what we call a generalized FEM shape function. So this is given in this equation and illustrated in this figure. So here at the top, we have a linear FEM shape function defined on this patch of quadrilateral elements. In the middle, we have a generic enrichment function E. And at the bottom, the GFEM shape function computed from the product of these two functions. Now, to select the enrichment, typically we use a priori information available about the problem. For example, if now we have a crack in that patch of element, a crack cut in the patch of elements, instead of modifying the mesh to fit that line, represent the crack, we enrich the nodes of the element cut by the crack by a discontinuous enrichment like the one illustrated here. So in the case of fracture, which is our focus here, we use three types of enrichments: polynomial, discontinuous, the one that I just showed to you, and also singular enrichment functions close to the crack front. We know that close to the crack front, this is the behavior of the solution, so why not use that? Is freely available information. So this, again, reflects the a priori information we have about the solution of this class of problem. So that's the basic idea. But what else do you need to actually use this method to solve, let's say, real-world problems? So I'll list here what we use in our solver in particular, the main ingredients that we use. The first one is mesh adaptivity. I believe that this is a must-have if you are interested in 3D problems with non-planar fractures that you don't know a priori what's the fracture path. It's not feasible to create a fine mesh in a huge volume where that volume would contain the fracture. So this animation is just a simple illustration of the application of this adaptivity, where you see the elements being refined and refined as the crack propagates, and also the dynamic assignment of enrichments. Red nodes are enriched with discontinuous function, the heaviside function I showed earlier, and the yellow nodes are enriched with the singular functions. Another important, let's say, ingredient that I believe you need is quadratic or even cubic approximation sometimes. I think low order, like linear approximations, they do not really give a satisfactory approximation in general. And you can see these in practice. Everybody nowadays, common practice to solve finite element, using finite element method to solve problems using quadratic approximation. There is a reason for that. Another regarding approximation, I believe that's important to use enrichment function, singular enrichments in a region around the crack front that is not just on elements that are cut by the crack front, but in a finite region around the crack front. We call that geometrical enrichment. And what's the benefit of that? If you use this approach, which is shown here and here, you can get optimal convergence, which means that the convergence is controlled by the order of approximation, not by the strength of the singularity on the crack front. So with that, you can get much more accurate solution than with the standard finite element method. So that gives the approximation part, but we also need to guarantee stability, control the conditioning of the stiffness matrix, for example. And for that, we use what's called the stable generalized finite element method with discontinuous interpolant, which is a concept developed in my group. What this boils down is simply to modify the enrichments that I showed you earlier, such that they lead to good condition. And I think that's now well understood. And we have shown that with this strategy, we can control the conditioning. We're using quadratic or cubic approximation and geometrical enrichment. Now we need to apply this to a problem, and we are interested in complicated fracture geometries in 3D, so you need a way to represent these surfaces. These are 3D fracture surfaces. I'll show some simulations on this later on. So this is pure computational geometry. This is not really related to GFEM, but anytime you need to solve a problem with a sharp fracture, non-planar sharp fracture, you need to somehow represent them. And finally, if you are interested in stress density factors, linear elastic fracture mechanics, you need to compute stress density factors. So how to extract them robustly and efficiently? We have been using the displacement correlation method, but for that to work, you need all these above. We need good approximation and so on. And with that, we get very accurate stress density factors, less than 1% error, but we need all these for this to work well. And last but not least, we need to parallelize. So every computer nowadays has multiple cores, right? Even your cell phone has multiple cores. So we need to take advantage of that. And for that, we use OpenMP. So that's in a nutshell, let's say, the technology that goes together with the basic ideas that I mentioned to you earlier. All right, having that, let's now look at a validation of this methodology using everything that I just showed to you. So this slide illustrates an experiment that we have used for the validation of the mathematical model that I have just described. So in this experiment, fluid is injected in a wellbore that is connected to a fracture that is initially planar. Q sub I is the flow rate that is injected here, and sigma sub L is the confinement stress applied to this system. And interactions between the fracture front and the free surface cause the fracture to turn away towards the free surface as it propagates. The amount of turning is controlled by this ratio, where again here sigma L is the confinement and K1C is the fracture toughness of the rock, and H the distance of the initial fracture, distant from that to the free surface. So here we have two limiting cases. The first one is when this ratio is 0, which happens when there is no confinement. That leads to the maximum turning. The other limiting case is for large values of this ratio. And in that case, the fracture you propagate on a plane. So this slide shows the experimental setup, and here the material and fluid properties used in the experiment and also in our simulations. So in this experiment, here this is the specimen, this is a cylindrical specimen. This is the initial flow connected to a pipe that is connected to a pump that you inject the fluid under pressure and cause the fracture to propagate towards the free surface. This plot shows the fracture inflow rate, the amount of fluid entering the fracture as a function of time. And you can see that in the early stage, there is this very sharp transient of fluid flow, which is much higher than the pump rate, which is about this value here. And this is due to the compressibility of the system. Before the fracture propagates, you are pumping fluid in the system, and because of compressibility, this is stored in the system before the fracture propagate. And you need to consider this in your simulations. If you neglect this, you're not going to be able to predict the experimental results. So this is the cylindrical specimen subject to confinement. And because of symmetry, we model only a quarter of the domain and apply symmetry boundary conditions on these two planes. And this is a close-up in the Wellbore region with the initial fracture, which is of the size of 1 millimeter. Now we solve this problem without confinement. Remember that this is the case that leads to the maximum fracture turn. So this animation now shows the evolution of the fracture surface as we pump fluid into the fracture cavity. And you can see that indeed, as discussed earlier, the fracture propagates towards the free surface. And you can see that we get a very nice axisymmetric shape, even though we use a fully 3D solver. And for that, you require fairly accurate stress density factors. So this again, a figure showing the end of the simulation. So let's see next how this compares with the experimental results. So this plot shows the normalized generalized FEM and experimental fracture path. In the horizontal axis, we have the normalized fracture radius. In the vertical axis, the normalized distance from the fracture front to the free surface. So this is a picture of the experiment and the location where data was collected. So these 4 points give this cloud of data shown here in this plot. And you can see a very good agreement between experimental data and the predicted fracture path using generalized FEM. And this plot shows the evolution of the fracture radius, evolution as a function of time. Again, GFEM and experimental results. And again, excellent matching between the two for a non-planar 3D fracture. And finally, this is the pressure at the wellbore, also measures as a function of time between comparing GFEM and experiments. Again, fairly good matching of the results. So we are happy with that. So with that, we can move to an application. But before that, let me explain how we handle now multiple fractures. So we saw how to solve a problem with one fracture, but in our application, we have several fractures propagating at the same time. So as the fluid is injected in the wellhead, the fluid will be partitioned among the fractures at a given stage. And the amount of fluid entering each fracture is not going to be exactly the same. The amount of fluid entering each fracture will depend on the fracture size, the fracture geometry, as we discussed earlier, and also on losses at connections between the wellbore and the fracture. So a way to estimate this fluid partition is to model the wellbore. In addition to the fracture, we model the wellbore and the connections between the wellbore and the fractures. So let's see how we did that. So in this slide, we have an illustration of a wellbore in this grayish cylinder shown here. And this is the mathematical, 1D mathematical model of the wellbore. This in blue is the fluid FEM mesh of the fracture surface, where we are going to have a fluid flowing. And in pink, you have the connections between this 1D model of the wellbore and the 2D model of the fracture surface. So these dimensions here are just for illustration, does not mean that the connection is of this length, it's simply that we use a 1D model, and we have to connect that 1D model to a 2D model. And so this is how we have in the code, but physically, this is not what we have in reality. So for the flow in the wellbore, we use the Huygens-Poiseuille flow, which is given by this equation. Q sub W is the flow in the wellbore, RW is the radius of the wellbore, and PW is the pressure in the wellbore. Mu is the viscosity of the fluid. And for the pressure drop at the connection between this wellbore and the fracture, we use the classical sharp edge orifice equation, which says that the pressure drop is given by the square of this quantity, A times the square of this flow. And this quantity is given by ρ, which is the fluid density, and is the number of perforations connecting the wellbore and a fracture. D sub P is the perforation diameter, and C sub D is called the discharge coefficient. So these are empirical relations, and we could use other ones, and so, but that's the one we have adopted. All right, having that, let's now look at an application. The simulation of propagation and interactions of transversal fractures near wellbore. So in this problem, we simulate three fractures that are initially planar and perpendicular to a horizontal wellbore, shown here in green. Here we have the direction of the in situ stress. This is the maximum and maximum horizontal and minimum horizontal. So the direction of the minimum in situ stress is also called the preferential direction for fracture propagation. So this is the direction that, if we have the wellbore aligned with this direction, we will require the least amount of pressure for the fractures to propagate, because you'll be pushing against the least confinement that you have in this reservoir. So we would like, again, to align this green line with this direction. However, in practice, we do not know exactly what is this direction of the minimum in situ stress. This is thousands of feet below, and there is some uncertainty about this direction. And even if we knew exactly that, I think it's not practical to expect that you can drill the wellbore exactly along that direction. So it's reasonable to assume that in practice, there will always be some misalignment between the wellbore and the horizontal in situ stress, the minimum in situ stress, which is the preferential direction that you would like to have. So the goal of this problem, of this simulation, is to investigate the effect of this misalignment. What's the impact of this on fracture shape, and also the pressure that we need to use to propagate those fractures. So we solve the problem using no misalignment of the fractures. 5 degrees and 10 degrees, just small misalignments. So even those small misalignments, are they relevant? What's the impact of this misalignment? So these are the parameters adopted in the simulation, the parameters for the solid and the fluid. This is water, and these are the parameters for the wellbore, as explained in the previous slide. Okay, so this video will show the simulation for the case with 10 degrees of misalignment, which is the highest misalignment that we have considered. So I'll stop here to highlight that the outer fractures, they now have a different shape from the middle one. And also this blue fracture is propagating more to the left, while the yellow one is propagating more to the right. So this misalignment is causing this loss of symmetry between the outer fractures. So let's continue, and I'll spin the fracture so you can better see what I just described to you. So stop one more time, and you can see that what I mentioned earlier is even more pronounced now. And this has some practical implications, in my opinion. Here, this is the wellbore, and so if you are pumping proppant, the proppant will go through the wellbore to the fracture. And this proppant is used to prevent the fractures from closing after you remove the fluid pressure. And so for this fracture shape, the proppant has to travel much farther in this direction than it has in that direction. So this may have some impact on how you design these proppant, how you select which type of proppant, and so on in practice. So let's spin this to see the shapes of the fractures at the end of the simulation. So fairly complex 3D shapes, which means that we really need 3D simulations to capture this type of response, this kind of geometry of the fractures. 2D simulation is not possible to capture this with 2D simulations. So this is now a superposition of the shapes of the fractures when you have no misalignment, 5 and 10 degrees of misalignment. In blue, we have the 5-degree case. And you can see that just 5 degrees leads to fractures that are fairly different from the no misalignment case, which are shown in green. Again, showing the importance of perhaps considering these in practical applications. So I'll spin this so we can see the shape of these fractures that are certainly fully 3D in nature. Okay, and this plot shows the wellbore pressure evolution for the 3 fractures. This is for the lateral fractures. They have the same profile, even though their shape are not the same, but the type of anti-symmetry kind of they have leads to the same pressure profile. And this is for the middle fracture. And we can see that with 10 degrees of misalignment, we clearly need higher pressures at early stage to start the propagation of the fractures, which again, this has potentially practical implications, for example, in design the pumping system. You want to make sure that you can reach the pressure required for fracture initiation propagation. So with that, let me summarize what I have presented so far. I presented a fully 3D GFEM to simulate simultaneous propagation and interaction of multiple fractures from a wellbore. For that, we need to solve a couple nonlinear time-dependent multiphysics problem in 3D. We have verified and validated the method, and we have adopted many things to make the method computationally efficient, such as mesh adaptivity, high order approximation, while still controlling the condition. So I think this is important for, again, solving difficult practical problems. And we show that we are able to capture 3D effects of misalignment between wellbore and in situ stress. And if you want to know more details about all these things, these are available in these references here. And if you cannot access them, just contact me. So with that, let's move to the second part. And for that, let's go back to our target application, which is multi-stage hydraulic fracturing from a horizontal wellbore. So predictions, computational or analytical predictions, even using very sophisticated models, are of course affected by the many uncertainties about the subsurface. So how to account for those uncertainties? So there are many ways to do that. One idea that we have been exploring in collaboration with ExxonMobil is to use the information that we may collect from one stage to perhaps improve the computational model and the parameters used in the next stage. In other words, take advantage that we are solving this problem. We are performing this treatment in multiple stages, and we want to use information at one stage to perhaps improve the next stage. So for example, it has been postulated that if we can infer the fracture shape at a given stage, we could perhaps improve the model parameters and the treatment parameters used in the next stage. The question is how to quickly infer fracture shapes during this treatment and at a low computational cost. So that's the subject of the second part of my presentation. So that's what I mentioned earlier, the uncertainties about the subsurface limit the predictions. Perhaps we can infer the shape. The question is to improve the treatment, but now the question is how to do that at a low cost. So this slide, well, it has been, again, as I mentioned earlier, postulated that fracture geometry may be inferred from the analysis of pressure transients in a wellbore. So in this figure, we have a circular fracture that is open and connected to a vertical wellbore. So both the fracture and the wellbore, they are filled with fluid. Now, suppose that a pressure pulse is generated at the wellbore head. So this pulse will travel down and back multiple times through this wellbore. And interactions between this pulse and open fractures connected to the wellbore, you change the frequency and attenuation of that signal. This is illustrated in this figure. Again, the attenuation and changing frequency as this pulse travels down and back into the wellbore. And it has been postulated that this signal can potentially be used to infer the shape of the fractures connected to the wellbore. For that, to do that, it's required to simulate wave propagation inside of the fracture and in the reservoir around the fracture. And that's what I'm going to focus next on this box here, where I'm going to simulate this wave propagation problem. So guided waves propagate along a fluid-filled fracture are known as Kraukl's waves. And these are waves in which the phase velocity approaches zero as the frequency approaches zero. And they are highly dispersive. There is a strong attenuation in these waves. And this type of wave have been applied in several fields, for example, to study magma-filled fractures, flowing in fractures in glaciers, and also to infer the geometry of hydraulic fractures in oil and gas industry, which is the focus here. So this is an example of a Kraukl's wave simulation, just to give you a heads up what's coming next. This is the elastic waves propagating the reservoir. These waves are created by the dynamic opening of the fracture that is here. And this dynamic opening is created by pressure pulse, fluid pressure pulse propagating in this fracture cavity. So our goal is to develop a generalized FEM methodology to solve this multi-physics problem. So let's start with the equations governing wave propagation in the solid. So in this presentation, we are assuming that the solid is a reservoir with a fracture that is filled with fluid. So this is a circular fracture connected to a horizontal wellbore, and this is a cross-section of the fracture. And here I have the reservoir, and here we have the confinement stresses. Wave propagation in the reservoir is governed by the classical wave propagation equation. These are the boundary conditions on the fracture face, which is there is a traction here that is given, that's created by the fluid pressure. We also need to account for shear stresses, and this is done in the fluid equations, as I will show next. These are the initial conditions for displacement and velocity. So classical equations at this point. But now let's look at the fluid equations. The first one, it represents a conservation of mass and continuity of velocity at the fluid-solid interface. So imagine that we have a fracture here in the embedded in the solid, and that interface between the fluid in the fracture and the solid, there must be a continuity of velocity, and that's what this equation represents. K sub F is the bulk modulus of the solid, sorry, of the fluid. These are governing equations for the fluid. P is the pressure in the fluid. V average is the width average fluid velocity, which is computed using this equation. W naught is the initial fracture opening, and V we now integrate to the thickness to get this average velocity through the thickness of the fracture. Z is the transversal direction, or Z bar is the transversal direction of the fracture. So W naught, as I mentioned, is the initial fracture opening, and W is the fracture opening that comes from the solution of the wave equation that I showed earlier. That's the first equation that we need to solve. The second one is written here and represents conservation of momentum and solid-fluid interface equilibrium. So Rho naught is the initial fluid density. The fluid is compressible, so this is the initial density. V average is given here. P is the fluid pressure. Mu is the fluid viscosity. And these are the other quantities that I have already defined. So with this average, we have now to solve a problem on a 2D surface in 3D space, a 2D manifold in 3D space. So let's look briefly at the boundary conditions. So we typically adopt two types of boundary conditions for the fluid problem in the fracture. The first one is pressure that is typically prescribed at the fracture mouth, which is where the fracture is connected to the wellbore. We can apply a pressure sharp like the one illustrated here at the fracture mouth from the wellbore. This comes from the wellbore into the fracture cavity. The other type of boundary condition is zero flux on the fracture front. So along this front here, there is no fluid leak. So this means that the normal flux in the normal direction to the boundary is zero. These are the initial opening and initial pressure that we can get that from the simulation of the hydroelectric fracture propagation. So at this point, the fracture propagates and is now, let's say, reached its final shape. Is no longer propagating, so we can get what's the fracture opening and the fluid pressure at that point from the simulation we did earlier. And we assume zero initial velocity for the fluid. Okay, so now let's look at the weak form of those equations. So this slide, you show the weak form of the couple equations after time discretization. So for the solid, we use a Newmark method for the discretization in time, which leads to this equation here. After we discretize in space, these you lead to the mass matrix, these you lead to a stiffness matrix. And this is a coupling term that accounts for the pressure that comes from the fluid equations. And this is the right-hand side, which is kind of a long equation, so I'll leave this out. Now let's look at the fluid equations after time discretization. We use the alpha method for time discretization of the fluid equations. And that leads to these two equations shown here. Again, pressure that we compute by solving the fluid equations is used in the solid equations, coupling the two. The other coupling term comes from the opening. This opening that is needed in the fluid equations comes from the jumping displacement across the fracture surface that is provided by the solution of this equation. All right, so that's the system of equations in the weak form. We discretize in space now, and that leads to this fully coupled system of equations, which is fully coupled but linear. So we only need to assemble and factorize these ones. In the case of hydraulic fractional propagation, was a nonlinear system, but here the system is linear. So we can solve for a fairly large number of time steps very quickly, and that will be needed later on, as you see. So these are the entries in this matrix. These are standard terms that you get from Newmark method. This is now not so standard, but I don't have the time to go into all the details. I will refer you to this reference that hopefully will be available soon. All right, so having that, let's see how well this works. Let's solve a verification problem first, so we can check our formulation and implementation. So in this problem, we have a layer of rock under plane strain conditions. We solve using a 3D model, but apply constraints in the transversal direction to mimic plane strain condition that was what we have the solution for in the analytical case. So this is a zoom in the fracture region where we have the finite element mesh for the fluid. And the boundary conditions are the same as I explained earlier, and zero flux, the normal direction. And in the fracture edge shown here in red, we apply this pressure pulse. And these are the properties of the rock and the fluid. So now in this slide, I'll show the evolution of the solution fields. Here you see the waves propagating in the solid. And here you see the dynamic opening of the fracture that exists here. And here will be the evolution of the fluid pressure in the fracture cavity. So we see the waves propagating from that region caused by this excitation of the fracture opening and closing. I should say oscillating, caused by this pressure wave propagating into the fracture. So highly coupled problem that we need to solve in a monolithic manner, as I showed earlier. So now I'll show next phase velocity. Before that, let me define what is phase velocity. This is defined as the velocity at which a certain frequency wave travels in a domain. So in this animation, this red square is moving with the phase velocity, as if you are riding a wave and your velocity is the phase velocity. So on this plot now I have the phase velocity of waves of different frequencies traveling in the fracture cavity. And we did computations for 3 choices of the initial opening of the fracture, W0. We considered 10, 3, 1, and 0.5 millimeter. And we have a comparison between GFEM and analytical solution from this reference. And they agree very well for all frequencies and all choice of W0. So with that, we are happy. And so we move on to a validation of this model. So for that, we work with our collaborators at ExxonMobil. They perform experiments at their facility in New Jersey. And so I'll report next comparison between their experiments and our simulations. So this figure shows a simplified representation of the experimental setup at ExxonMobil. This in green is the solid domain. Inside we have a fracture showing red. These are the dimensions. And there were 3 experiments where the difference between them is the dimensions, slightly changing dimensions, but also in the initial opening, which is important for the behavior of these calculus waves. And here we have the material properties and fluid properties. The material is an acrylic and the fluid is a glycerol. So this is the GFEM model with the 3D mesh shown in green. If we cut the domain, we can see the mesh. There's a finite element mesh for the fluid. And the boundary conditions are similar to what I showed earlier. No fluid flux, the normal direction along these blue boundaries of the fracture. And at this edge of the fracture, pressure pulse is prescribed. We consider, I believe, 4 pulses with 4 different frequencies. Here I'm showing 2 of them. They have a 0.71 and 1.16 hertz. Now I will show the animation of the pressure evolution for the excitation with 50 hertz. So this is the evolution of the, again, the pressure in the fracture cavity. I'll play one more time. So note that very strong attenuation of these waves. Shortly after it enters the fracture cavity, it decays quite quickly. And that's one of the characteristics of these Krautless waves. Now on this plot, I have again phase velocity as a function of the frequency. And we have the result for the 3 experiments I indicated earlier. So in glyphs, we have the experimental data. And these bars represent uncertainty from the measurements. And in solid lines, we have the GFEM results. We have 2 lines for GFEM because there was some uncertainty about the material properties. And so the 2 lines represent the upper and lower bounds for those material properties. And we can see fairly good agreement in all 3 experiments that we have simulated and compared with the ExxonMobil results. Included here in this dashed line, this is the 2D analytical solution that assumes that the problem is a plane strain problem, which seems reasonable at first because the domain is very simple, a rectangular domain. You could imagine, can I solve this as a 2D plane strain? So this curve here shows that the answer is probably not. Even in this very simple domain, 3D effects are important. With that, let me move to my last example, which is to simulate wave propagation now on this elliptical fracture. So this is very similar to my first example. The main difference here is just the shape of the fracture. Instead of rectangular fracture, I'm using an elliptical fracture, which is more realistic in practice. They want to see what's the impact of change in this shape in some quantities of interest. These are the properties, the same as I show in my early example, where I have a rectangular fracture, and the length of the fracture is also the same as before. So these are the boundary conditions, same as before, and this is the on this blue edge, and for the red edge, we use the same pressure pulse that we used earlier, but we apply only in part of the edge, which is more realistic since not the whole fracture is connected to the wellbore. So now this is the evolution of the fluid pressure in the fracture cavity. And you can see very smooth solution, strong gradients, but no spurious oscillation. And again, fairly smooth solution for the pressure. And I stop here to highlight that even though the magnitude of the pressure, the maximum magnitude of the pressure pulse prescribed along this edge is 0.7, the pressure inside of the fracture actually gets much higher values than that. And that's caused by resonance inside of the fracture cavity, and also the shape, this elliptical shape that focus the flow into a smaller and smaller region, causing this behavior that I show here, this resonant behavior. Again, fairly smooth evolution of the pressure in the fracture cavity. Now let's look at some more quantitative data. We are going to look into the so-called fracture transfer function, which is given by this relation. So this quantity represents the amount of fluid that the fracture can take for a given pressure fluctuation at the fracture mouth. So if I excite the fracture, if I given frequency, how much fluid can enter that fracture? And the maximum of this quantity identify this resonant mode in the fracture. These are these spikes shown here in these curves. The amplitude has a maximum at those locations. And here we are comparing these spikes, these resonant frequencies for the two fracture shapes. Everything the same, essentially the same, but with different fracture shapes leads to fairly different resonant modes, which indicate that potentially this could be used to infer the geometry of the fractures, solving an inverse problem. And that's something that we may pursue in the future. So with that, let me conclude and summarize what I have presented. I have shown a fully 3D methodology to simulate waves in fluid-filled fracture. The method is stable. We demonstrated this in this reference. I did not have time to show that here today. We have verified and validated the method in these references. We show that 3D effects can be important even for simple fracture shapes like rectangular fractures, and that the method now allows the analysis of more realistic geometries than it was before available in the literature. And the GFEM is ideal for inverse problems because we do not need to fit a mesh to an evolving fracture that is evolving during this optimization, this inverse problem. So we can create one model for the reservoir and let the GFEM solver take care of the rest. So with that, I would like to conclude and also to acknowledge the contributions of current and former students and postdocs. I also like to acknowledge my collaborators at ExxonMobil and also the financial support from ExxonMobil to this research. With that, thank you very much for your attention, and this is my contact information, and I will be glad to take any questions that you might have.
Well, thank you very much, Professor Duarte. That was indeed a very insightful presentation. So we are open to questions now. So we will keep the floor open to questions from any attendees or panelists. So we in the Q&A box. So if you would like, you could answer that. That's from Mr. Pawan Bhukia, who's a student at IIT Madras.
That's what if we use finite difference schemes for time discretization? Well, we actually use finite difference for time discretization. Newmark method and alpha method are finite difference schemes for time discretization. And is Newton-Raphson method used? Yeah, in both part of my presentation, we use finite difference in time. For the first part, we use a second part, as I mentioned, was Newmark and alpha method. For the first type was backward Euler. And okay, is Newton-Raphson method used for solving nonlinear FEM formulation? We use a modified Newton for the first part where we have a nonlinear problem. For the second part is a linear problem. And what's the advantage of solving the couple formulation using staggering approach? Well, when you have a staggered approach, there are issues because the fluid equation that you solve, I'm talking about the first part of my presentation, that's a Neumann problem. So you don't know the value of the pressure, you only know flow, which is a Neumann boundary condition. So that's one of the issues with a staggered scheme, that you now have to deal with this not well-defined Neumann problem. When you couple that Neumann problem with the problem for the reservoir, which has Dirichlet boundary conditions, we have proved that when you couple the system, now the problem is well-defined and has a unique solution. So that's, I think, one of the challenge for staggered scheme. And we have adopted the monolithic approach because of that. The second question is, how would these models work for salt dome structures? We don't have experience with that. I think that's more like an interface problem. I don't know actually much about that. I cannot really comment much on that. How sigma H and sigma sub H are determined? Well, I don't know exactly in practice how that's done. I believe that they actually create some sort of a small fracture. Professor Detornay knows much more about that than me. And somebody, Dakshina is also here, I think. But I assume that somebody from the industry is going to give me that information. That's my answer. And okay, the next question is, have you simulated the plasma pulse fracturing? What information about the reservoir can we obtain from the waves? No, we have not looked into plasma pulse. That's an interesting technology to use some dynamic waves. And we have some ideas related to that, but we have not actually done that. And information about the reservoir, we have not tried to solve inverse problems to infer, let's say, geological formation in the reservoir. We are looking only in the geometry of the fracture, not the reservoir itself. And now from Tao Jin, the first part of your talk, you use LEFEM for fracture propagation, which is appropriate for toughness dominated regime. For fluid viscous dominated fracture propagation regime, solid toughness might become relevant, and these will be large negative fluid pressure near the fracture tip. For example, in the KGD and penny-shaped crack. In this case, how does the method handle this challenge? That's correct. You can get negative pressure close to the crack tip, but does not mean that you have a fracture interpenetration. We prevent that in our algorithm. Whenever we have, let's say, a negative pressure, our algorithm will prevent that interpenetration from happening. And regarding the high viscosity, you're right, that you change let's say, the physics of the problem. It's a boundary layer problem, has been shown by Professor Detornay's group, that you have a boundary layer and the size of the square root of R singularity changes with these the parameters that you are using in your simulation. So the higher the viscosity, the smaller the region where you have the square root of singularity. And we use mesh adaptivity to be able to capture even small regions where you have the square root of R singularity. We cannot go to zero, but we can get to capture solve problems with very small regions where you have the square root of R singularity. I hope that I have answered your questions. Is there any other open questions, Chandra?
Yeah, I think Professor Detournay is asking if your code is capable of simulating cases where the fluid front is distinct from the crack front, as is the case for shallow hydraulic fractures.
No, we have always assumed that there is no fluid lag. In other words, we have assumed the opposite of what you have mentioned, that we have fractures deep in the reservoir. Yeah, no, we cannot handle that case. We now need to find where is the fluid front and the fracture front. Those will be, that will be beyond the scope of what we have at this point.
So looks like we have another question. So they're asking if your GFEM method can simulate CO2 injection induced seismic wave propagation modeling in a faulted aquifer system. So it's a very specific question. I think it looks like the title of their project.
Yeah, it's an interesting problem and very challenging for sure, and also relevant to the industry. There are many situations where you have these seismic issues, not just because of CO2 injection, but also sometimes gas extraction and other situations. So we have not looked into that. Now we have, we have this framework, we can add the physics, but it is already fairly complicated as it is. So we try to focus on a specific set of applications, and that is doesn't include this class of problem that you mentioned.
So I think we have another question. This is from Swapnil, and they're asking if the negative pressure near the crack tip is due to any mathematical lag in the model.
Mathematical lag? No, I think you can get it even with the analytical solution. You get this negative pressure. It's part of the physics. I think it's not an artifact, if that's what he means.
Okay, so I think that covers.
Well, in reality, yeah. So just to follow up, you could have such a negative pressure that you, let's say, you have now the fluid become change phase from to vapor, but that again, that will be even more complicated physics that you need to consider. Phase change because of this negative pressure that may be possible in reality. Yeah, sorry, Chandra, I interrupt you.
No problem. Yeah, so I think that covers all the questions in the Q&A panel. So I will maybe pose this once again. So are there any further questions from either the attendees or the panelists?
Hello, Professor Duarte, it is Abhijit. I'm Chandra's colleague.
Hello, Abhijit, nice to meet you.
Yeah, I'm working in the Department of Applied Mechanics. Yeah, it's a very insightful talk. I mean, we are working on similar problems, but anyway, a bit lagging far behind. So I am interested to see what into seismicity and hydrofracking as well. So my simple, I mean, I didn't understand many of the things probably very well. So your second part, you are mainly talking about the wave propagation simulation in a fluid, right? So second part, there is, I mean, my question is mainly, did you simulate any kind of wave generation while hydrofracturing is happening or crack is propagating?
No, we did not look into that as a source of waves. We assumed that there will be a pressure pulse coming from the wellbore, and this can be generated by some artificial source, or it can be an effect of what's the so-called water hammer. If they are pumping fluid at very high flow rate, and if they close the pumping system quickly, that will generate a wave that will propagate in the wellbore and cause what's called the water hammer, and that is let's say generated let's say not with artificial source, but by this effect of this water hammer effect. That's the type of sources that are typically used when we talk about Kraukl's waves, or the waves that you would maybe some acoustic waves as the rock is breaking. That is something that we have not looked into that now. That will be now waves emanate from the fracture front, from what I understand.
Yeah, but do you think it is important? I mean, it will be very significant that can be felt on the surface, ground surface?
Well, perhaps that's from what I understand in practice, they will use these acoustic emissions to find out where is this fracture going, at least have an idea where are these propagation developing by trying to find out where the sources, the acoustic sources in the subsurface exist. At least that's one potential application of identifying the location of these sources. But I don't know what else could be used. So we have not looked into that.
Okay. Thank you very much for your answers. Okay. Thank you so much.
You're welcome, Jit.
Okay, thank you.
Okay, so do we have any further questions from either the attendees or the panelists?
Yeah, hi, Chandra.
Yeah, go ahead, Ramesh.
So hi, Duarte. It was an excellent talk. So I just have one quick question. So this acoustic emission measurements, possibly you might be able to get it from the field studies, right? That sort of predicts how the wave or fracture propagation is happening in the field. So if you have those sort of field results, did you try to validate your or try to compare your GFEM results sometime?
No, because we are not predicting those kind of emissions. We are, let's say, the Kraukl's wave is not really emission of waves from the system itself. The excitation comes from the wellbore and into the fracture cavity. So there is no, at least, I'm not aware that the calculus wave itself, you create any seismic emission in the fracture front. Because at that point, the fracture is no longer propagating. The fracture is static, and the fluid is moving back and forth inside of the fracture cavity, but the fracture is no longer growing. So there is no material being broken at the fracture front, and that's when the seismic wave can be emitted as new fracture surface is created. That's not the case in the fracture, in the fluid fracture simulation.
Okay. Thank you.
Okay, so thank you, Professor Duarte. So I have a couple of questions. So first of all, this presentation that you made is probably one of the most advanced GFEM simulations that I've seen. You know, the non-planar 3D finite element simulations for crack growth that they're showing are really phenomenal.
Thank you.
Thank you. So some of the challenges that I have faced when using these kinds of methods, especially in 3D, is that how do you accurately compute these stress intensity factors when one crack, let's say, merges into a pre-existing fracture? And, you know, then if you want to discuss its evolution, you know, on the other side of this pre-existing fracture or an interface. So do you have, you know, difficulties doing that, or, you know, is this displacement correlation method, does it work well in those situations?
Yeah, displacement correlation has a property that is, let's say, an advantage for this kind of situation, because imagine that you have a fracture here and I have another one here, right? That's the situation that you were mentioning. And now if I use, this is my fracture front, and I want to use a domain integral method to extract the stress density factor, I need to create an extraction domain ahead of my crack front. But my crack front is getting close to that other fracture. I cannot fit an extraction domain ahead of my crack front. But with displacement correlation, the quants that we compute are behind the crack front, are on the crack tail. So we measure the opening in the fracture, not ahead of the fracture. So because of that, you could extract even when this is very close. So in that sense, DCM is more robust than domain integral methods because of this inherent limitation. You cannot fit your extraction domain when you have now one fracture too close to each other. Your extraction domain cannot cross the other one. That will be invalid.
Right, but when the crack merges, then isn't there like a sudden change in the displacement, even behind the original crack tip?
Well, yeah, that we actually did some crack merge in the past, but not in the context of hydraulic fracture. We had a project with the Federal Aviation Agents to look into reflective cracks in airfield pavements, where they have many cracks propagating from the bottom of this overlay, asphalt overlay, and they merge at the bottom. And for that type of crack, they all propagate on a plane, and they merge on the side. They do not merge like this. So they all are from the bottom going up, and this guy grow, and then they merge together and keep going up. And I never published that work. Why? Because we can do the simulations, but I don't know if the physics is correct. Why? Because when these two cracks are very close, LEFM is not valid anymore. You are going to probably have some damage that you develop between these two very close fractures, and they are not going to get to a nano distance and then merge. They are going to merge at some finite distance. And which distance is that? I don't know. We need some fracture criteria to tell me that. GFEM is a discretization method. So we never published that. Well, that is part of the dissertation of a student, but we never published as a paper. We compare with experiments, but it's qualitative, not quantitative. I cannot quantify because how to merge. That's a fracture mechanics question. And that, let's say, maybe phase field can answer that, but you have to pay a price for that, right? You know.
Sure, yeah. So I have a related question here again, is that when you go from, let's say, one layer to another layer, right? I mean, let's say you have heterogeneity in your domain. So in that case, again, your solution behind the crack tip is not necessarily reflective of how it will be once the crack penetrates into the neighboring layer, right? So at the interface, are there challenges with prediction of the stress intensity factors?
Yeah, you have to take in account for that. There is some theory, there is some work. I forgot the name of the author. He was in Harvard some years ago. That's an interface problem where you have a crack, again, going through this interface as you described, and then the asymptotic, because all these methods are based on asymptotic solutions. So you need to know what's the asymptotic solution when I have an interface problem. Domain integral method, all these auxiliary functions, they are based on some asymptotic solution. So it does not matter if you use DCM, domain integral, or you name it. Most of them, from what I know, they use some information about the analytical solution. And when you have an interface problem, that change. So you need to take that into account. If it's let's say, an interface like you were describing, but in shale, you have actually many layers, but they are not very thick. They are thin layers. And perhaps you can homogenize that to an equivalent anisotropic material, transversely anisotropic material. And in that case, we have developed techniques to extract the stress sensitive factors using DCM on anisotropic material, homogeneous but anisotropic. If I would go to, depends on the problem. Is this somebody asked here about the salt domes? Now that's one interface that is different from one you have a layer in the shale that is, again, many little thin layers of material that was deposited over time, and they have this direction dependent property that is something we have not considered, but the framework can address that for sure.
Okay, so thank you once again. I think I really enjoyed your presentation, and thanks for joining us for this webinar series, and we look forward to staying in touch.
Well, thank you for the invitation again, and for the opportunity to share with you and your colleagues and the audience the work of my group. It has been a pleasure.
Thank you so much.
Thank you.
Thank you, Professor Duarte. Yeah.
Bye, everybody. Have a good evening, and thanks for hanging around.
Thank you.
Thanks. Bye now.
Bye-bye.